This lesson is about rates of change. We will be talking about two types of rates of change. The first one is the average rate of change, and as you'll see, we have a small formula that we will be using, which is AROC as an average rate of change. It'll be f of x2 minus f of x1 over x2 minus x1, which is exactly the same as something you've seen for the past few years, the slope equation of a line. So this is the slope equation of a line, and that's m equals y2 minus y1 over x2 minus x1. So we're replacing y2 by f of x2. We're replacing y1 by f of x1. In this case, our slope of the secant is the same as the average rate of change, as you'll see in the diagram below. So we have 2 points on a graph, and if we find the slope of the line passing through those two, which we will call a secant, that would be the average rate of change. We're given the example here, given a function f of x equals x squared. Find the average rate of change from x equals 1 to x equals 2. So the 2 points that I have given here in an example are at x equals 1 and x equals 2, for example. And it's simple application of x values. So f of x2 minus f of x1 over x2 minus x1, the equation we see above here. So we'll have the x2 is the value 2. That will be considered as x2. And the x1 will be the value 1. So we just substitute those values in our average rate of change equation. The function f represents the square of any value. So whatever we have as an x value, we have to square it. That is the function. And in this case, since x is 2 in the first expression, f of 2, then we have 2 squared minus f of 1, so we have 1 squared, over x2 minus x1, which is 2 minus 1. Simplifying that expression, you get 4 minus 1 equals 3 as your average rate of change. The second type of rate of change we have is the instantaneous rate of change. This one is an estimation. It is, for now, not an accurate value, and that's the reason I use the approximation sign. And we build it from using the average rate of change equation, this one here. So it's f of x2 minus f of x1 over x2 minus x1, but we do a small change to help give an approximation, the best approximation possible to make it an instantaneous rate of change. By definition, the instantaneous rate of change is the slope of a tangent at a point. So we don't have the ability right now to find the slope of a tangent at a point algebraically. So what we'll do is we'll assume that we're finding the average rate of change for between 2 points that are very, very close. And so here I have 2 points drawn. These should be, or the idea behind them is that these are a magnification of 2 really close points separated by an infinitesimally small decimal h. And that's why I write for the first point x as its coordinate. For the second point, I write its coordinate, the x coordinate, as an x plus h. So there is a difference of h between the first point and the second point. Now, in applying this expression, we'll write, instead of f of x2 minus f of x1 over x2 minus x1, we'll write here f of x plus h. That's your x2. And instead of x1, we'll write f of x. And here again, instead of x2, we'll write x plus h. And again, x instead of x1. For estimation purposes, because we don't want to use a really long decimal, we will use h as a 0.0001. that's good enough to give us a really good approximation. Now the equation becomes instantaneous rate of change approximately equals f of x plus 0.0001 minus f of x over 0.0001. Notice how in the equation above, top of this page, you'll see how in the denominator x plus h minus x, the two x's cancel out and you're left with h, and that's why in the denominator here I only have 0.0001. We're going to take an example. We'll use the same function, f of x equals x squared, and find the instantaneous rate of change at x equals 2. Notice, for instantaneous rate of change, we have a particular x value. For average rate of change, as we've seen in the previous example, it had to be a rate of change from x equals 1 till x equals 2. So there must be an interval to find the average rate of change. So we're going to use that equation, the approximation. The IROC is approximately equal f of x plus h minus f of x over h. X is given to be 2, so we replace x by 2 in these two expressions. And h is 0.0001, so both h values get replaced by 0.0001. Again, the function is the square of the value. So whatever the x is, we're going to square it. In this case, your input is 2 plus 0.0001, which means your value that you're going to square is a 2.0001 minus the value in f of 2 is, so 2, we're going to square that over 0.0001. Squaring 2.0001 will give us 4.00040001 minus 4 over the 0.0001, and your final answer is this, 4.0001. The accurate slope of the tangent, so the accurate instantaneous rate of change will be, so from like using derivatives and calculus, of f of x at x equals 2 is actually 4. And look at the really close approximation we have found. Later when you learn derivatives, you will find the exact value for the slope of a tangent or the instantaneous rate of change. Have a good day.